Hello everyone. As Maciek mentioned, I am Michał Sęk and I am working as software engineer at Software Mention, and I would like to talk about Web Audio API, which is yet another browser-based audio processing library or media processing library. So for the context, for the more than last year, I have been working on a library called React Native Audio API, which aims to port Web Audio API to React Native ecosystem. And that gave me a glimpse how it works internally and how it sometimes doesn't work. So I would like to share that today. But let's start with the basics. So what actually is Web Audio API? And it is a powerful audio processing engine, which is built around the idea on our audio graph, where we can connect different nodes to create an audio processing pipeline. And at the base, there is interface called audio context. Thanks to it, we can create various nodes, connect them together, and the simplest use case of web audio is probably source node connected through some effects to destination. So for example, we have something reading from a file, going through gain node for volume control, and finally it flows to the device speakers. But of course, we are not limited to single processing lines. We can play multiple sounds at the same time, chain multiple effects, or in some cases, we can even loop the signal. So in web audio, there are three types of nodes that we can use. First one is our source nodes, which act as an input to the system. As example, we can use oscillator, which is able to compute simple tones. Audio buffer source node that can play short audio files, and media element source node that can read data from existing somewhere on the page audio or video tags. Then we have processing nodes, which provides a way to modify the sounds or have an information about what is currently playing. And as example, we can use big filter node, which provides equalizer-like filters, delay nodes, which works like an echo, or dynamic compressor node, which can scale up or scale down the signal going through the graph in order to avoid, for example, clipping or some distorted sounds. Finally, there is an last node that is destination, and usually it is connected directly with the hardware of the system. Another important aspect of Web Audio API is timekeeping and scheduling. It is able to provide us an sample accurate scheduling. So in comparison to audio tag, when we have to tell the audio to play now, or we are hoping for the best that it aligns up with everything else that is happening in the application. Here we can schedule the playback start or stop exactly to fractions of a second. So with keeping that in mind, let's check on the basic example. As I have explained at the beginning, we have to start with creating an audio context first. And for this case of this example, we have to obtain the audio data somehow. Here we can simply fetch it. Then finally, using the decode audio data method of an audio context, we have to decode that, and this will make it available for the entire audio system. Then we can finally create our first source node, which in this case is audio buffer source node, and attach the buffer to it. Finally, we can connect it to the destination and start playing. Where I have the cursor, here it is. And it sounds like something like this. Okay, so in comparison to using just audio tag with single source property, it is a bit more of code to write. So let's see what we can do with it. So what happened? Okay, so imagine we want to modify the sound to sound like played in some large production hall, and to achieve that we can use our first processing node, which in this case will be convolver node. As name suggests, it computes linear convolution between two signals. The one is the song that is flowing through the graph. The second one we have to provide as an impulse parameter, and it is just another audio buffer. Here, for simplicity, we can assume we are filling it, for example, with random values. Then, in order to really modify the song, we have to connect this convolver node in between the source and the destination tag. And the effect sounds like this. Okay, that's almost perfect, but let's see what we can do more about that. So in such case, we probably wouldn't hear also as much as of the higher pitch sounds. So let's get rid of them. And we can do that with another processing node, which is called BQuad filter, already mentioned. We'll use that type of low-pass filter to cut off all frequencies above certain threshold. And like previously, we connect it between the previous node and the destination. The effect sounds like that. Okay, so the sound is a bit too quiet for one to hear it probably. So let's fix that in the final step of the example, and we will use another simple processing node, which in this case is already mentioned gain node. And we will just use it to bump the volume of the entire signal. So the final results sound like this. Okay, but from the beginning of this example, there was one line of code that not necessarily is optimal in real life, and it is not only there because I had to fit everything on the single screen. And it is that every time we want to call onPlay function, we have to create a new audio buffer source node, attach the buffer to it, and finally start it. If you would try to start it for the second time, we'll just get an exception telling us that we don't want to. And this is weird, like having the node stored somewhere that we can reuse every time we want to fire the same exact sound. Wouldn't be like more optimal and performant? And to answer that, I have to explain how Web Audio API works under the hood. But before that, and let's start that the core part of underlying audio engine is an audio thread, which will constantly process the sound. Most important parameter for it, which probably here everyone is familiar with, is ensample rate, which tells how many frames or values for each channel of the sound are within 1 second of the sound. So in the modern devices, the most common value is 44.1K, which means we have to produce 44,100 values for each channel in each second. And of course, going through entire audio graph that user created for each frame would be super slow. So usually the modern audio engines works in batches. In case of Web Audio API, we are talking about batches of 128 frames each. This means that to provide real-time audio experience, we have to traverse entire graph 375 times each second, or provide one batch of the frames in under 3 milliseconds. And this creates some limitations or what we can do on the audio thread itself. And so the first one, probably most important one, is that we can't really allocate any new data there. Everything must be prepared somewhere else and provided to the audio thread beforehand. Second one is that any kind of locking or synchronization method are also forbidden. If the audio thread would have to wait for something, the underlying device system would cut off the thread, making the sound glitch. And the third one, probably obvious at this point, is that tasks not related to the audio processing should be avoided there. So keeping that in mind, let's take a look at some simple naive approach. So let's say we first would require the user to allocate every resource he wants to use in the audio plane, then create a plan that what should happen with the entire audio from start to the end. And finally, the user will be able to hit some kind of play method or just play button. This way, we meet all of the criteria. Everything is created on the JavaScript thread, so we don't really have to make any new allocations on the audio one. So this one is met. We also have everything pre-planned, so we don't really need to synchronize between the threads. So we also don't need to use any locking mechanism. And lastly, we are just following the plan, so we don't really need to notify anyone or just do any additional data. But with such approach, there's one major issue, and it is not real-time API anymore. So, but here we could argue if the real-time aspect to planning the sound and shaping how it would work is really necessary, such API, and as probably you can guess, yes. Let's imagine a music learning application where first we have to react to anything that user presses on the screen. Secondly, there is some backing track playing along with it. So each time user hits some note, with the naive approach, we would have to stop the sound, create the new pipeline, including the sound that we want, the note we want to play for him, and finally start again. And maybe with some hacks, someone could be able to make it seamless for the user. But let's get one step further and imagine some bullet hell kind of game. Here, we wouldn't be able to provide responsive enough audio. So now let's take a look how it is done in modern browsers as well as React Native Audio API. So first, we have to get back to the idea of budget frames. Here we can, for simplicity, call it render blocks. And then, just like in the naive approach, we require the user, or actually the API itself enforces that every resource is created on the JavaScript thread. Since from the perspective of the JavaScript thread, allocations is a really quick and simple operation, so we don't have to worry about that. Then when user tries to connect some nodes or start playing at some time, we treat those commands as timeline events. And it gives us two advantages. One of which is that we can, thanks to that, we can keep the order of the commands exactly as user called them. Second one, we can easily enforce or use the time requested by the user in some of the commands, for example, like start. And then those commands will be moved to the audio thread in between the render blocks. Thanks to that, we won't be modifying the audio graph when it is processing the sound, which would again create some glitches. And in the next step, let's check how the graph is modified in between the render blocks. So here we have some already active playing graph. And there are two source nodes. One is connected through some effect node and both goes to main volume control and finally to destination. Then user allocates some new resources, which for us, from the audio thread perspective, at this point doesn't mean anything because we don't have any connections or stored calls. But in the same time, one of the already existing nodes stopped playing. So we are marking it as safe for the allocation, which being done on yet another thread, just to avoid also the allocation itself on the audio thread. Okay, then user will finally send us some comments about connections, and those will be executed one by one, modifying the graph. And finally, since the last operation was a disconnect, there is one already existing node that can be safely marked for the allocation, moved to the construction thread, and removed. Okay, and that's it. Sums up the overall overview how the base audio graph processing algorithm works. But let's take also a look at another aspect in the Web Audio API I find a bit weird. So audio context has a property called current time, and it is expected from the users that they will be using that for tracking anything that happens with the audio, as well as scheduling the events. But in contradiction to its name, and everything I could find on the internet, it is not really a time. So the audio context itself tracks how many frames it has processed since the beginning of its creation. And the current time property just returns that value divided by sample rate. So if we would compare this value with, for example, something from performance now or even date now, they would probably misalign but at the same time, the audio context current time is more useful in terms of scheduling because we can, thanks to that, we can calculate the exact frame we want to start the sound, which in many cases is a must, for example, music applications. And I find it super weird that it is not stated anywhere, because I've seen a lot of people misusing that property or starting or scheduling nodes with just the time obtained from date now or performance now. And to sum up, the Web Audio API is powerful and flexible audio engine, which provides ability to create simple playback, create some complex effects, or creates full interactive audio applications. But it does with some share or its own quirks. Some parts of the interface are a bit weird, especially if you don't know the internal implementation. But everything is dictated by either having to work on real-time audio or by simplicity of the interface. Since nowhere in the example we really had to know what the DSP is. And this makes the Web Audio API really work. The design is performance-driven, and it remains accessible for almost every developer, no matter his audio engineering expertise or not. So it might be a bit strange, but is engine that really makes the web sing. Thank you.
Thank you, Michał. Are there any questions about the presentation? I don't see any hands, so there is a question on my mind. wasn't touched on necessarily on the presentation, but I do know that you've been working on porting this API to React Native mobile world, and I'm just wondering if the constraint of the mobile world just exacerbate all of the issues that are already there, or quirks, or it's like a smooth sailing more or less, or is there anything that surprise you or blow your mind?
Actually, on the mobile, because in the web browser we don't really deal with that device itself. We just have the browser. In the mobile world, another important aspect of the audio are, for example, lock screens integrating with other applications, and so on. And this is another kind of weird world when nothing is really documented well, and you have to guess everything for yourself.
Okay, all right. So good luck with that journey. You will probably need it. Let's thank Michał with another round of applause. Oh, there was a question. I'm sorry.
I had a question. Is it on? Yeah. I was wondering how you implement things like the autoplay policy, like this, the curse in the browser that you cannot really play anything on the audio context unless you initialize it with a user click. Did you do that, or did you just ignore that for now?
We have ignored that part,
Okay.
although we provided an property not existing in the Web Audio API, which can tell the engine to not start on the creation, because we don't have that constraint on the mobile world.
Thank you.
My eyes are terrible, so if I did miss another one.
How do you, hello? How do you achieve proper multi-threaded processing? If you're building a large mixer with many nodes, how to do it properly? It's quite a
It
question.
is a tough one. So most of the nodes reside only on the audio thread. There are some nodes, for example, like the one I have mentioned, which is convolver node, which inside them, they kind of use multi-threading. But most of the simpler ones are just using the audio thread. And in terms of convolver node, we haven't really finished its implementation, so I can don't have yet an insight how it works.
Thanks.
Okay, I think that I'm not doing this service to anyone wanting to ask a question anymore. So another round of applause.